Welcome back to our series on exoplanet hunting methods. Today, we look at another widely used and popular method of exoplanet detection, known as the radial velocity aka Doppler spectroscopy method. The hunt for extrasolar planets sure has heated up in the past decade or so thanks to improvements made in instrumentation and methodology. The number of exoplanets discovered as of December 1, 2017 has reached 3,710 planets in 2,780 star systems, with 621 systems boasting multiple planets. Unfortunately, due to the limits astronomers are forced to contend with, the vast majority have been discovered using indirect methods. When it comes to these indirect methods, one of the most popular and effective is the radial velocity method, also known as Doppler spectroscopy. This method relies on observing the spectra stars for signs of wobble, where the star is found to be moving towards and away from Earth. This movement is caused by the presence of planets, which exert a gravitational influence on the respective sun. Description: essentially, the radial velocity method consists not of looking for signs of planets themselves, but in observing a star for signs of movement. This is deduced by using a spectrometer to measure the way in which the star's spectral lines are displaced due to the Doppler effect, i.e., how light from the star is shifted towards the red or blue end of the spectrum. Redshift, blueshift. Diagram detailing the radial velocity aka Doppler shift method. Atlas Cumbres Observatory. These shifts are indications that the star is moving away from redshift or towards blueshift Earth. Based on the star's velocity, astronomers can determine the presence of a planet or system of planets. The speed at which a star moves around its center of mass, which is much smaller than that of a planet, is nevertheless measurable using today's spectrometers. Until 2012, this method was the most effective means of detecting exoplanets, but has since come to be replaced by the transit photometry. Nevertheless, it remains a highly effective method and is often relied upon in conjunction with a transit method to confirm the existence of exoplanets and place constraints on their size and mass. Advantages: the radial velocity method was the first successful means of exoplanet detection, and has had a high success rate for identifying exoplanets in both nearby Proxima b MTRAPPIST1, S7 planets and distant star systems CORO 7c. One of the main advantages is that it allows for the eccentricity of the planet's orbit to be measured directly. The radial velocity signal is distance independent, but requires a high signal-to-noise ratio spectra to achieve a high degree of precision. As such, it is generally used to look for low-mass planets around stars that are within 160 light-years from Earth, but can still detect gas giants up to a few thousand light-years away. http://planets.nasa.gov interactable 11 vid radial_velocity.mp4. The radial velocity technique is able to detect planets around low-mass stars, such as M-type red dwarf stars. This is due to the fact that low-mass stars are more affected by the gravitational tug of planets and because such stars generally rotate more slowly, leading to more clear spectral lines. This makes the radial velocity method highly useful for two reasons. For one, M-type stars are the most common in the universe, accounting for 70% of stars in spiral galaxies and 90% of stars in elliptical galaxies. Second, recent studies have indicated that low-mass, M-type stars are the most likely place to find terrestrial, i.e. rocky planets. The radial velocity method is therefore well suited for the study of Earth-like planets that orbit closely to red dwarf suns within the respective habitable zones. Another major advantage is the way the radial velocity method is able to place accurate constraints on a planet's mass. Although the radial velocity of a star can only yield estimates of a planet's minimum mass, distinguishing the planet's own spectral lines from those of the star can yield measurements of the planet's radial velocity. This allows astronomers to determine the inclination of the planet's orbit, which enables the measurement of the planet's actual mass. This technique also rules out false positives and provides data about the composition of the planet. The main issue is that such detection is possible only if the planet orbits around a relatively bright star and if the planet reflects or emits a lot of light. Number of extrasolar planet discoveries per year through September 2014, with colors indicating method of detection: radial velocity blue, transit green, timing yellow, direct imaging red, microlensing orange. Credit public domain. As of December 2017, 662 of all exoplanet discoveries, both candidates and those that have been confirmed, were detected using the radial velocity method alone, almost 30% of the total. Disadvantages. That being said, the radial velocity method also has some notable drawbacks. For starters, it is not possible to observe hundreds or even thousands of stars simultaneously with a single telescope, as is done with transit photometry. In addition, sometimes Doppler spectrography can produce false signals, especially in multi-planet and multi-star systems. This is often due to the presence of magnetic fields and certain types of stellar activity, but can also arise from a lack of sufficient data since stars are not generally observed continuously. However, these limitations can be mitigated by pairing radial velocity measurements with another method, the most popular and effective of which is transit photometry. While distinguishing between the spectral lines of a star and a planet can allow for better constraints to be placed on a planet's mass, this is generally only possible if the planet orbits around a relatively bright star and the planet reflects or emits a lot of light. In addition, planets that have highly inclined orbits relative to the observer's line of sight produce smaller visible wobbles, and are therefore harder to detect. In the end, the radial velocity method is most effective when paired with transit photometry, specifically for the sake of confirming detections made with the latter method. When both methods are used in combination, the existence of a planet can not only be confirmed, but accurate estimates of its radius and true mass can be made. Radial velocity surveys. Observatories that use the radial velocity method include the European Southern Observatory's Solar Observatory in Chile. This facility conducts exoplanet hunting surveys using its 3.6-meter telescope, which is equipped with a high-accuracy radial velocity planet searcher HARPS spectrometer. There's also the telescopes at the Keck Observatory in Mauna Kea, Hawaii, which rely on the high-resolution ECL spectrometer HIAS spectrometer. There's also the Haute-Provence Observatory in southern France, which used the LED spectrograph to detect 51 Pegasi b, the first hot Jupiter found to be orbiting a main sequence star, in 1995. In 2006, LED was decommissioned and replaced by the SOFI spectrograph. Exoplanet hunting surveys that rely on the radial velocity method are expected to benefit greatly from the deployment of the James Webb Space Telescope JWST, which is scheduled for 2019. Once operational, this mission will obtain Doppler measurements of stars using its advanced suite of infrared instruments to determine the presence of exoplanet candidates. Some of these will then be confirmed using the Transient's Exoplanet Survey satellite TESS, which will deploy in 2018. Thanks to improvements in technology and methodology, exoplanet discovery has grown by leaps and bounds in recent years. With thousands of exoplanets confirmed, the focus has gradually shifted towards the characterizing of these planets to learn more about their atmospheres and conditions on their surface. In the coming decades, thanks in part to the deployment of new missions, some very profound discoveries are expected to be made. Sources. Matt Williams is the curator of Universe Today's Guide to Space. He is also a freelance writer, a science fiction author and a taekwondo instructor. He lives with his family on Vancouver Island in beautiful British Columbia. Doppler effect, exoplanet hunting, featured, Proxima b, radial velocity method, transit method, TRAPPIST1.